Hello, everyone. I think one day I'll probably get used to saying hello, everyone, just looking at a computer screen, but not yet. Anyway, today I have section 4.1. We moved into chapter 4. Chapter 4 deals with more derivatives. So far, we've just taken derivatives of pretty basic things, functions, simple functions, polynomials. We use the quotient rule, the quotient rule, the power rule, the product rule. We get some trig functions. So now we have probably the most important and maybe hardest one to understand, which is called the chain rule. The chain rule gives us a way to deal with like a function inside of a function. So in other words, it gives us a way to deal with f of g of x. So we have one function inside of another. For example, something as simple as this. Back in the last section, if I asked you to take y prime, we have a power rule, yeah, but the power rule only tells us how to deal with x squared. And it says that, hey, if I have a power rule and it's x squared, I just do y equals 2x. Pretty simple, no problem. But it doesn't work unless it's x. So if it's a whole function of x, like in this case, the 2x plus 2, we have to do something different. If this problem had shown up last chapter, we would have just had to multiply this out. 4x squared plus 8x plus 4, and then take the derivative term by term. We don't want to have to do that every time. Or even something as simple as this, y equals sine of 2x, right? We have a formula that tells us how to take the derivative of sine x, for instance. The derivative of sine x is cosine x, but it doesn't tell us what to do if it's the derivative of sine 2x, right? So this section, erase this for a second here, gives us a way to deal with a function inside of a function. So there's two ways to look at this, and hopefully you remember this. And what I'm about to show you can be a little tricky at the beginning, but once I do examples, I think you'll get it. But basically, we have one function inside of another function, right? So we have y equals f of g of x, all right? So what I've done is I'm going to split those up, right? So I'm going to just say y is equal to f of u, but u is g of x. So if I take that g of x, plug it into there, I get that. So we're going to separate them into two functions. I'm going to show you a nice, quick, easy way to find those derivatives, but this is kind of the formula for how you do it. So we're going to do is separate them into two functions. So I'll just go back to this really basic one where I had sine 2x. What that means is y we're going to call sine of u, because that 2x is inside, it's the composite piece of it, and we'll just call u equal to 2x. It's the inside part. These two little formulas here and here tell us how to do the chain rule. So they're both telling us the same thing, actually. The second one's the one we're going to use a little bit more. First one just says the derivative, which is dy dx, equals dy du. So if we go to my problem here, dy is sine u, right? So the derivative of sine u is cosine u. Sorry about my writing there. I had to write up the top there. And then times du dx, which is the derivative of the inside part, which is 2x, but the derivative of that 2x is a 2. And now we substitute that u back, and we get 2 times the cosine of 2x. So that's kind of how the chain rule works, is you take the inside part, pull it out, you leave the other function by itself, you take the derivative of this one, take the derivative of that one, and multiply them together. But that's a nuisance, okay? If you have functions inside of functions, it's not going to work. And if you got long functions, it's not going to work. So we're going to look for a little quicker way rather than doing it this way. And this is kind of what this does. Right here it says f of g of x prime. So what we're going to do is, should be parentheses there, just take f prime of g of x. In other words, we're going to treat g of x as if it's an x. So notice it just says f prime of g of x. So we just kind of ignore the fact that it's a 2x inside of there instead of a 2, and then we do that. And then we take the derivative of g. So let me do a little erasing here. I'm going to show you the same problem. Sorry, I got a little bit messy here. We're going to do the same problem, but we won't look at it this way. We'll look at it this way. So now this is sine of 2x. In this case, what we're going to do is we're going to take that 2x, and just for a second, I just call it a box, actually. I just say we're going to treat that like it's an x, okay? So if I asked you what the derivative of sine x is, you would tell me cosine x, hopefully. So now I'm just going to say x is just a variable, right? So we have this little formula. Let me go back down here that says if y equals sine x, y prime equals cosine x. But x is just a variable, so I said if y equals sine of box, I know that sounds silly, but I'm going to do that a lot because it's going to help you organize things, then y prime is just cosine of that box. Okay. Now, if it's a chain rule, then we have to go back and take the derivative of the box. So watch if we go back here. All right, derivative of sine 2x, we treat that like it's a box. The derivative of sine box is cosine box, but that box is 2x. So it's cosine 2x. And now, second step, go back and multiply by the derivative of that what's inside that box, which is your 2. Okay. Don't worry about simplifying derivatives for now. You can just leave it like that. It's totally fine. So that's, in essence, the chain rule. I'm going to just do 3 or 4 examples a little bit quickly, I hope. If you already got that, so I'm going to do parametric equations in just a second. You can fast forward through my examples if you want, but the examples I think are pretty important. So I got a 1, 2, 3, 4 examples. Some of them are longer than others, so I'm just going to go through them relatively quickly. Notice I'm throwing some trig functions in there. Just because we just did the trig function. So again, we're doing sine of x squared plus x. So sine of box, the derivative of sine of box is cosine of that same box, works just like the last problem. And now we got to multiply by the derivative of what's inside that box, which is the derivative of x squared plus x, which is 2x plus 1, just little power rules. So all you got to do, stop, you're done. Same thing here. So now we got a little double whammy here. We got 2 composite functions, actually. We got the tangent of something and the sine of something. So it's tangent of box, derivative of tangent. I hope you remember secant squared. So it becomes secant squared of that same box, 5 minus sine 2x. So that's the tangent box, derivative of secant squared box. Now we have to multiply by the derivative of what's inside that box. The derivative of that 5 is 0, minus, now I have the same issue again. Now I have sine of circle. Change my variables for you there, my pictures. So the derivative of sine of something is cosine of that same thing. Okay. And then I got to multiply by the derivative of what's inside that circle, which is the 2. Sometimes it's easy to forget little parts. This takes a lot of practice, and I know watching this in the video can be a little bit tricky. So I'm going to do a couple more examples. I'll go over lots of problems in class also. The power rules can be a little tricky because people don't see the powers. This is sine to the 5th power. I like to write that. Oh gosh, sorry about that. Let me get out of that. I like to write that as sine x to the 5th power. Okay, that way I can think about what's inside. So now this is like box to the 5th power. So we're going to treat the inside part. Remember, the first thing you do in a chain rule is you take the inside part and you just treat it like it's an x. Same thing you would have done if it was an x. If I just said x to the 5th, you would say the derivative is 5x to the 4th. So I'm going to say the derivative is 5x to the 4th, but it's not x, it's sine x. So it's 5 times sine x to the 4th. And now I have to go back and take the derivative of what's inside the box. The derivative of that sine is cosine x. Okay. And then I'm going to do the same thing on this last one. I'm going to rewrite this tangent of sine squared. This is a little bit more complicated. I'm going to rewrite this all to the 1/2 power. So again, it's box to the 1/2 power. So the derivative of that would be power rule first, 1/2 times everything that's inside this box to the negative 1/2. So tangent of sine squared of 5x plus 2x. Now I have to take the derivative of what's inside that box. I'm going to change colors for you here. So it's tangent of something. So I'm going to go same thing I did in the last one. It's tangent of, we'll call that ellipse. I don't know if it's ellipse or not. So the tangent of something, the derivative of that tangent something is secant squared of that same something, or of the ellipse. Okay. I'm going to run out of space here, so I'm just going to kind of go down to the bottom here. Now I have to take the derivative of what's inside that box, right? Or I'm sorry, inside the ellipse, which is a sine squared 5x plus 2x. Those are 2 different terms. So I have this sine squared again. We'll go back to box. It's like sine, I'm going to write this over here, sine of 5x squared. just like we did on that last example. Fifth power, so this would be 2. Drop that power, sine of 5x, all to the first. But remember that 5x is a circle. It's another composite function. This is a nice long drawn problem. So times 5. I got this last little plus 2x left right here. So it's a plus 2. That was probably a little more complicated than the last one than most of them you'd see. But chain rule can be a little tricky when you have more. Just think about the boxes and circles. I think it can be pretty helpful pulling things apart. Hopefully that's enough to kind of get you started there. The last thing in this section is parametric equations. You did some work in parametric equations last year. Parametric equation is when you write y and x in terms of a other variable, a third variable. And typically that third variable would be t for time, which is us. So we have two functions. Y is some function of time. X is some function of time. If someone asks you to find the derivative or the slope of the tangent, same thing. It's really simple in parametric. Little formula right here. dy dx is very simply dy dt over dx dt. So you take the derivative of y and divide it by the derivative of x. Pretty straightforward. Nothing too tricky. So here's an example. X equals secant t, y equals tangent t. Sometimes they give you parameters on these parametric equations. Doesn't really matter for our purposes. It's just what the graph would look like. But it's between negative pi over 2 and pi over 2. You can kind of ignore that. What's this? And the actual question is just to find the derivative at negative pi over 4. They might actually ask you to find the slope of the tangent line, which I'll go one step further, I guess, and do that. And then I'll be done. Let's go to purple here. So it's very simple. dy dx is just dy dt over dx dt. If I were in a regular class, I'd probably prove, by the way, why this works. It's the connections of the parametric equations to the rectangular equations, but trying to prove something in this would take a little longer. And we're just going to try to move along a little bit. So the dy dt is the derivative of y. The derivative of y is tangent. So the derivative of that is secant squared t. And then dx dt, the derivative of secant is secant t tangent t. I do a little simplifying, cross out that secant. And I get secant t over tangent t. I could probably even simplify that if I wanted to. I could leave it like that too. It doesn't really matter. It is the derivative. So if I plug in, or if I simplify, secant, I guess, is 1 over cosine. Tangent is sine over cosine. So those cancel. Cosines, you wind up with 1 over sine, yeah, which is a cosecant. And then I ask at negative pi over 4, quick little trig review, I guess, cosecant of negative pi over 4. Cosecant, again, is a reciprocal of sine. The sine of pi over 4 would be root 2 over 2. So negative pi over 4 is down here. Sine is negative in that quadrant. So this is negative 2 over root 2, because it's the reciprocal of the cosine, which is, or the sine, which is root 2 over 2. That's about it. If I asked you to find, I'm going to just finish up real quick here. If I asked you to actually find the equation of the tangent line, you just take this pi over 4, plug it in there, and you get your x and your y. And then you just put it in point slope form. So y minus, plug in the y, which is the tangent of negative pi over 4, which is going to be tangent. That quadrant is negative, so negative 1 equals the slope times x minus the x value. The x value is secant of negative pi over 4, which is a root 2 over root 2. Sorry about all the hard trig stuff in that. Didn't really mean for that to happen there, but that's how you deal with parametric equations. So hopefully that's enough. Parametric and chain rule. Chain rule is tricky. Do a lot of practice, and we'll catch up in class the next day. See you later.